is very big in comparison to the moon. However, that is actually very small compared to what we might expect to see in the outskirts. And so what I'm about to show you now is what happens when we look in the outskirts. We can only now look in the outskirts because we have the technology to do so. What this means is taking big cameras on big telescopes, big digital cameras and big telescopes in order to see the actual stars. Then you find all the types of stars you're interested in. Then you make big maps of what's the star map look like, and then you show it here. But it's actually only been possible now, because you notice that's 15 degrees. That's the size of the full moon. So this is a very, very large image. The HST image that I showed at the very start, remember, a pinhead is effectively the size of this. So this is a completely wide field imaging. It's a very different type of thing. Now, when you look at it, that is actually what the Andromeda Galaxy looks like. What we're effectively doing by looking at very adjusted stars and by looking at star maps is looking much, 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 much fainter than you could do by making a traditional image of the galaxy. Okay, you have to be able to identify individual stars, and then you have to be able to make density maps effective of where the stars are to understand what's going on there. And that's what you see. And immediately you can see that, holy cow, galaxies are a bit bigger than we think. And galaxies are quite big in the first place. So, this is something that is still not even, I think, appreciated by astronomers. It's still not really appreciated even by me, that to actually look at, to be sure that you're looking at a patch of sky that's nothing to do with a galaxy that you see there, you have to look incredibly far away, because galaxies stretch out. Galaxies have stars far, far farther out than you might otherwise believe. What's very neat, of course, then is, well, what else do you see other than the fact you see anything there? What do you see? And you see streams, you see blobs, you see, in fact, lots and lots of overdensities, and I'll come back to those in a second. You'll notice around the Triangulum Galaxy, which is the thing down in the bottom left, all of a sudden, in fact, can I just go back? That's the Triangulum Galaxy. Now, you can see right all the way around its outskirts is this giant distortion of stars. You can see streams of stars which are stretching out humongous distances. I'm going to say some units here, kiloparsecs. Ignore the units. The point is this: we are 8 units away from the center of the Milky Way. Okay? Some of these streams of stars are hundreds, 200 units long. Okay, so that's much, 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 much larger scales than what we're normally used to dealing with, even when we're talking about galaxies. So the size of these things are truly vast, and the extent of the Andromeda Galaxy, and the Andromeda Galaxy is no reason it should be special. So by implication, most galaxies, we expect, stretch out at least this far. The amazing thing about, perhaps the most important thing I've taken away from this is we didn't go out far enough, because right at the edge of the survey, we're still finding stars that belong to the Andromeda Galaxy. So we could go out further, and we would find more. What's very neat as well, sorry, I'm just tripping up on wires here. What's very neat as well is all of these little and things are Andromeda 1, Andromeda 5, Andromeda 10, and so on and so on. The one which actually isn't published yet, I like to call Andromeda XXX. I think it sounds just kind of cool, quite frankly. I would like to be called Andromeda XXX if I was a galaxy, so Now, all of these are satellites. All of these are little dwarf galaxies associated with the Andromeda Galaxy. Okay? All of these are kind of just the equivalents to the things I showed you previously. These very, very faint things. None of these are quite as faint, because Andromeda is much further away. We can't see things that are quite that faint. But nevertheless, these are still very faint. When we started this, or when I was doing my graduate studies back in the UK, there we were looking at Andromedas 1, 2, 3, 5, 6, and 7 were the things that were known. Andromeda 4, nobody talked about. So there were basically there was 6 or 7 dwarf galaxies known around Andromeda. There's now more than 30, and by extension, by looking at the area of sky we've looked at compared to what we haven't, we expect it to be at least 100 as bright as what we're seeing here. Okay? Going down even fainter, there may be many hundreds. There's never going to be tens and tens of thousands, as you might expect from those simulations in dark matter, but there's many hundreds. So again, one of the neat things, I think, is that these are the closest galaxies to us, but it's becoming clear from the work that people here and elsewhere are doing on the Milky Way, are doing on M31, are doing in the local group in general. We're still actually discovering stuff. We still don't actually know all of the things out there. Okay, when I was doing my PhD, somebody said, well, what are you working on? I said, the Andromeda Galaxy, to which the response was, well, don't we know about the Andromeda Galaxy? And by all accounts, we should. We've been looking at it for a long time. But because of new technologies, because of sort of starting to look for different things, because our understanding of how galaxies are put together has evolved, we're now asking different questions, and we're able to answer them, if you like, in a different way. And we're discovering more and more things which we didn't know that we had to try to understand in the first place. And that's perhaps the most important part of it all. And this is a zoom-in of M33, the Triangulum Galaxy. And this is just an ugly-looking contour map, but just to show you the size of that big stream that's around M33, that big diffuse structure surrounding Triangulum. What could that possibly be due to? Well, we were wondering that too, and we don't know if this is the correct answer, but it's one we very much like. And that is, it looks, you remember when I showed you a dwarf galaxy orbiting around the Milky Way, and it was being pulled apart, and it was being pulled apart in kind of S-shaped type of way. The main body looked a bit more distorted, but S-shape. That's kind of like this. So maybe something's pulling it apart. And remember, the Triangulum Galaxy is actually a bit more massive than all these other dwarfs. It's 1/10 the size of the Andromeda Galaxy. So what's big enough to pull it apart? Well, in that region of sky, there's only one thing that we know about. It's called Andromeda. So is there a way to actually see, well, does that make sense? Because to be pulled apart, it would be needing to feel a strong effect due to the Andromeda's galaxy. How might that happen? Well, it works, if you do the numbers, it doesn't really work if it's just stayed at the position it's at now. You wouldn't expect it just to have always stayed where it is. But if instead you say, well, maybe at one point it was closer, passed by close to Andromeda, pulled out some of these stars, and it's now ended up in that position, then maybe you can do it. Okay, and it's just an idea. It's an idea. I wave my hands there when I describe it, but one way to show, like all these things, one can never show that it's right. I should say, on a tangent to all of this, one of the things I always try to emphasize is all of the stuff that I'm saying, all of these things about dark matter, all of these things about how we put galaxies together, I hope that you're getting the sense that, we're still figuring it out. Often astronomers, often scientists sort of get portrayed, perhaps some of them even portray themselves as we know the answer. We don't at all. We have ideas as to what they might be. We try out those ideas, and sometimes they seem to work. And if they seem to work, that's not that it's right. It's just that it's not obviously wrong. And that's science right there. Okay? Anybody who tries to tell you anything else is wrong. Okay? That's what science is. Okay? And as we test out things more and more, we become more and more confident. But all we've actually shown is not that it's right, just that it's not obviously wrong. Okay? It's not wrong until the next observation shows that it's wrong. So this also has a soundtrack, which I'm not sure if I should play or not. Perhaps I won't. This is Beyonce actually plays this one. I know it is. I think he got bored making them or something. So this is trying to show what is going on with Andromeda. So this is an earlier version of the map that I showed you, where you can see the distortion around Andromeda. So what we've said is, well, perhaps this was kind of the thing that was going on earlier on. M33 is orbiting around. It's a big galaxy, so it's going to orbit. It's a smaller galaxy, so it's going to orbit with the bigger galaxy. Earlier, it's passed close by to Andromeda. Because of that, it felt this stronger tidal effect. That you'll notice when it passed in front, the outskirts of that galaxy, M33, sort of extended, were pulled out slightly, and it's now falling back in. Such that the orbit through time is this. We happen to now be seeing it at the end point of all of this, but a few billion years ago, 2 or 3 billion years ago, it was, of course, at a different point in its orbit. It passes around in its orbit in front of Andromeda, not too close, because if it was too close, it would get completely destroyed. But it's not completely destroyed. It's only a bit messed up in the outskirts, which implies that any passage can't have been that close. Then from there, it passes right in front, and it now approaches. The nice thing about this is it reproduces qualitatively, more or less, what we see in terms of the structure, but we also know, of course, the relative positions of Andromeda and Triangulum now. And our simulation matches now. The relative positions now are where they should be. The velocities, how they're moving with respect to each other, are the same. The distances are the same. So it matches up a lot of stuff. Not right, but it's not obviously wrong. And it helps us perhaps make some guesses as to what's been going on in the history of this group, where we live, called the local group. So just to kind of summarize some of the things going on so far, I don't know if I pressed one too many. Yeah, I pressed one too many. Summarize some of the sort of take-home points, if you like. I mean, I'm trying to just give you a flavor for some of the things which we can do with nearby galaxies, which we can do by looking at stars. Remember, here, it's good for me, I have a fairly short attention span generally, so it's nice that you can do something as an astronomer, that you can do something with stars to try to understand galaxies, to try to make some contribution towards cosmology, that is understanding the universe as a whole. Okay, so that's sort of three of the main elements that people might think of when they think of astronomy. Nothing to do with planets. So if you can figure out how to get planets in there as well, then I'll be laughing, but I can't at the moment. So stars, galaxies, and cosmology. And the local group, there is a large number of galaxies there. They are a diverse system. Dwarf galaxies are there. They're thought to be highly dark matter dominated, makes them interesting in their own right. By looking at these dark matter dominated galaxies, by looking as well at how these, the stars, etc., distributed in the outskirts, we can start getting an idea of how the Milky Way, how Andromeda might have been put together. But the big uncertainty in all of that is really what's happening with the stuff that we can actually see in terms of the simulations. We understand dark matter, we think, in terms it can only interact via gravity. But what's going on with the gas? And that's something we really don't understand yet, and that's one of the things which we're trying to understand. This is a nice, rather beautiful simulation that I'll just show as I talk here, where you're not looking at the dark matter, but that's going on. Okay, that's going on, but you're just not looking at it. Here instead is another one of these simulations, but now they've put gas into it. Okay, so gas is the thing that makes stars. Stars are the things that make all the elements, and then so on, and then you get planet Earth, et cetera, et cetera, et cetera. So they've put gas into it to see how is the gas behaving as a result, and what's seeing. And you can start seeing how gas collapses into disks, which are presumably, in fact, they are at the center of the dark matter, though you can't see the dark matter here. Those disks actually rotate. This is due to a principle called the conservation of angular momentum. These things rotate, and then you have lots of merging going on, etc. Now, I have a colleague of mine who works in a different field of astronomy called looking at how stars form. And there they deal a lot with simulations as well from people who work on simulations. And his characterization of movies like this, which is grossly, unbelievably unfair, but maybe kind of right, is that if you, how did he put it? If you want to understand how rabbits behave, you don't watch a Bugs Bunny cartoon. Now, as Bugs Bunny cartoons go, this is kind of an interesting one. But the point is here, there's an awful lot of stuff we don't actually really understand. We think we kind of know how it probably works on average, but we don't have the computational power, we don't yet have the insight to really be able to model all of them properly, correctly, using all of the equations for all of the different physical processes that might be going on. So instead we say, well, if you have this much dark matter, then you probably have this much normal matter, and this much normal matter is probably going to produce this sort of fraction of stars, and that's informed by other observations. So it's consistent with our general knowledge, but you can see the sort of gross recipes for, if I have A and B, I'm going to get C. With C, if D happens, then I'll get E, and so on and so on. And that's essentially how these simulations are done. Grossly unfair, but in caricature, kind of correct. And so you can see that there is an understanding as to how you might get something like the Milky Way galaxy.